Hello everyone, I'm Bouvier and I'm very glad to make this video today with my colleague Baty for the JuliaCon 2022. First, on behalf of our team, we'd like to thank the organizers, and we're going to present to you today a package called InferOpt. It aims at using combinatorial optimization in machine learning pipelines. And well, it's a joint work with our colleagues Guillaume Dalle, Baty, me and Axel Parmentier at École des Ponts at the Cermix Lab. Well, you can access this notebook on this web page here. And well, first I'm going to introduce you the generic idea of the package with a few examples to illustrate it. Then I will add a bit of theoretical setting, and Leo will show you a tutorial. First, the question we would like to answer is, what is this package for? And well, you can have two distinct points of view. The first one is to enrich learning pipelines with combinatorial algorithms. That is to say that you want to leverage the structure of a combinatorial problem in a machine learning model. The second approach is to enhance combinatorial algorithms with learning pipelines. That is to say that you want to use predictions in order to ease solving hard combinatorial problems. Both can be illustrated with this kind of pipeline on the slide, where you have an initial instance that you pass through a machine learning predictor. Then you get an encoded instance of a combinatorial problem. You can solve it with any black box algorithm in order to get a candidate solution that you can evaluate in the end with a loss. And as you may know, the main difficulty with this kind of pipeline is to differentiate through the whole set of blocks, including the combinatorial algorithm that may be black box. And well, in our package, we provide a way to do so with a wrapper given any black box algorithm that can be used to solve mixed integral linear programs. We do so in two distinct settings, two distinct learning settings. The first one is learning by imitation, where you have a data set of instances and targets, for instance, solutions. But we also do this in a learning by experience setting, where you only have a data set of instances and a black box cost function to evaluate any given solution. The second setting is more challenging, and today I'm going to focus on illustrations of the learning by imitation setting. Just to tell you that we have many possible applications of this package, and we're only going to show you two of them today, which are the shortest path on Warcraft maps and the stochastic vehicle scheduling problem. If you want to have more, you can see the two-stage minimum spanning tree or a single machine scheduling problem with satellite package we can present you at the end of this session. Well, the first example is quite visual. It is shortest path on Warcraft maps. It was first introduced by Dalle et al. In 2020, and it is based on the following dataset, where you have both an image and a path. The image is a Warcraft map with different terrain types, and while it's more difficult to move in the water or in the rocks, for instance, than on the land. And the associated path is the shortest path from the top left to the bottom right corners. The learning goal is to recognize the terrain type in order to find the shortest path on new map images. Here I display again the learning pipeline, but specialized for the Warcraft example. At the beginning, you have an image map that you pass through a convolutional neural network with given weights, and then you get some predicted costs for the cells of the terrain. With those costs, you can apply a Dijkstra algorithm or any given shortest path algorithm in order to get a candidate shortest path from the top left to the bottom right corners. And the goal is to learn the weights of the convolutional neural network so that this output path is good. We do so with our InferOpt package in a learning pipeline, and here I illustrate some results on a test set image. So again, on the left you have the terrain map. In the middle you have the true costs that are given in the dataset, but they are not seen during training. It's just a way to know the true costs. And on the right you have the predicted costs, which are the outputs of our convolutional neural network. So you see that we managed to recover the structure of the costs. Here I display again the terrain map and both the label shortest path and the computed shortest path given the output of the convolutional neural network. And so you see that both of them they avoid the water and they're quite close. So here it was just an illustration of our package. Here is another example. It is a stochastic vehicle scattering problem to illustrate our package. So you have a set of tasks that are represented by the nodes on this graph and a set of vehicles to do those tasks. Each of them has a predefined time and duration. We want to decide the schedules of the vehicle's tools, and you have the constraint that all tasks must be fulfilled by exactly one vehicle. Why is it stochastic? It's because, well, once you've planned the tools, you reveal some randomness. It has an intrinsic random delay and a slack variable delay. So slack variable is due to the fact that you want to do task T before task U. The delay propagation equation is written on this slide, and the objective is to minimize the sum of the vehicle's costs, because the more vehicles you use, the more you pay, plus the expectation of the total delay cost. So it can be written as a mixed integral linear program here. It's a huge problem because you have many variables, which are the path here, and you can solve it with a column generation algorithm. What we want to do instead is to illustrate our package with a learning setting where we learn to approximate this hard problem with the problem on the slide here that you may recognize. It is a minimum cost flow problem. So more precisely, what we want to do is to learn the cost vector here, theta, of this minimum cost flow problem, so that when we encode the hard problem instance x with theta of x, we get a good solution with the minimum cost flow algorithm of the hard problem. It is illustrated here with the pipeline specified for this example. So we have an instance, we extract some features on each arc, then we can apply a generalized linear model to get the cost. For instance, here the cost for doing task 2 before task 6, which is the cost of this arc on the minimum cost flow problem. We encode this cost with a generalized linear model, given the features. Then we can solve the minimum cost flow problem to get a solution that we can use as a solution of the hard combinatorial problem. And here, what we do is we illustrate some results of delays. So again, the graph represents the task, and each path is related to one vehicle. On the left, we have the solution with a heuristic. On the right, we have the solution given a learning pipeline that was implemented with InferOpt. The size and the color of the nodes they illustrate the delay, the average delay, the expectation of the delay. And so you see that we managed to get smaller average delays on the learning setting than on the heuristic setting. And besides, the total cost is lower with this learning pipeline. So it's quite encouraging too to illustrate our package. Now, just a few theoretical background to illustrate learning by imitation and structured learning by imitation. Here is again the generic pipeline for learning through combinatorial algorithms. And as I mentioned previously, the argmax here, the mixed integral linear program argmax, is piecewise constant. And then you cannot have some gradient, meaningful gradient information. So what we can do, it was suggested by Dalle et al. And Baty et al. A few years ago, is to regularize this argmax with a convex function omega. And if we do so, we have a smooth argmax that can be differentiable, and therefore that we can use instead of the strong argmax in the learning pipeline. Here is just an animation to illustrate this procedure. So in gray, you have the convex polytope, the set of feasible solutions of the hard combinatorial problem. In red, you have the strong argmax, which moves from one vertex to another when you change the direction of the cost. And in blue, you have the regularized solution, which evolves smoothly. As you see, there is no jump from one vertex to another, and it's quite close to the strong argmax. So it's quite a visual way to illustrate our regularization in the InferOpt package. When we do so, we get a natural non-negative and convex loss, which is based on the regularization here. It's a Fenchel-Young loss. We can compute its gradients given a target solution and a parameter with this difference between the regularized argmax and the target solution. And then we can propagate gradients through the whole pipeline. So it's one of the ways we implement in the InferOpt package in order to differentiate through the whole pipeline. We have other ways to do it, both for learning by imitation and for learning by experience. Now, Leo will show you more about this package with a tutorial.
Hi, I'm Leo Baty, and I will continue and end this talk with a tutorial on how to use InferOpt to solve the following toy problem. We consider a dataset containing for each data point a graph which represents a public transport network and a shortest path representing an itinerary taken by the user. Our goal is to propose relevant paths for the user's future travels, and for this we need to learn the unknown user utility function. We'll build our data using grid graphs. A grid graph vertex corresponds to coordinates in a rectangular grid. A user can only move right or down to ensure a cyclicity, and the cost of a move is defined by the cost of the arrival vertex. So any grid graph can be entirely characterized by its vertex cost matrix. Here is an example of grid graphs in action. Here we define a random cost matrix. We define the associated graph, and we can compute easily the shortest path shown here. And we see that when theta varies, the shortest path also varies. So let's build our input data. We generate random instances, 30 instances with for each vertex 10 features. And we assume that the user combines these features using a linear function, and we define it here using chain and dense from the Flux library. And finally, we compute the unknown vertex costs using this unknown model. And then we can define our shortest path algorithm, which takes a cost matrix as input and computes the shortest path on this matrix. And we see that here we switch sign because the shortest path function computes a linear minimization problem, and the InferOpt by convention needs a linear maximization problem. So there is the switch of sign. And we use this shortest path function to compute the optimal paths taken by the user. Now we can start to build our InferOpt pipeline. For this, we initialize our model with random weights and a linear function. And then the first step to build an InferOpt pipeline is to choose a regularization. So we'll choose the perturb additive from InferOpt, which is a wrapper around the shortest path optimizer. And we see here a regularized prediction on 1 theta. What we see is that when we have no regularization, the regularized prediction is only one path. But when we start regularizing, we see that this prediction becomes a linear combination of several paths, which is smooth and interesting because allow us to define a differentiable loss. We can also increase the number of samples drawn for the regularization, which also increases the smoothness of the result. Now that we have the regularization, we can define our loss. Here we take the Fenchel-Young loss, which wraps the regularized predictor, and we obtain this object, which can take two arguments as input. The first one is the predicted theta, and the second one is the optimal path associated to the instance on which we predict. We see that the Fenchel loss is differentiable, which is what we want, and that's it. We have our full pipeline, full InferOpt pipeline, and we can now define our training loop. So here we will use the Flux library, but InferOpt is compatible with any Julia machine learning package that uses chain rules. So we trained for 200 epochs using our Fenchel-Young loss, and let's see the results. So here we have the loss evolution, and we see that it's decreasing, so the learning works, and we have a low final loss, which is good. And now let's check a more precise metric, which is the Hamming distance, the normalized Hamming distance, which is the average Hamming distance between the predicted paths and the optimal paths. And we see that it's also learning, and we have a very low final Hamming distance, which means that we predict almost for each instance almost the optimal path. So that ends the first part of this tutorial, and we'll see now the second part, which is what can we do if we also know the optimal cost, the user cost theta for datasets. In this case, we are in another setting, which is the smart predict and optimize setting, which gives us an additional loss to leverage this new information. So it's the SPO plus loss, which wraps our shortest path function. And this loss is also differentiable and takes as input an additional input, which is the optimal theta of the dataset. We can do the same for our training loop as before and check the results. And here we see that in a few epochs, the loss goes down to 0, which is perfect and means that for each sample, we predict exactly the optimal path. And if we check the Hamming distance, we should also have a 0 metric, which is the case. So in this second part, we managed to leverage additional information to increase the performance of our model. And finally, in the third part and last part of this tutorial, we'll see what can we do when we don't know the optimal path y and neither the optimal cost theta for our instances, but only have a black box cost function that can evaluate any given path. In this setting, named learning by experience setting, we still can do something. So here we have our black box cost function. And when we give it any predicted path, it gives us a cost value. So we can define a new loss, which is when you compose this path cost with the regularized predictor, we obtain a perturbed composition object, which can be used as a loss. And this loss takes only one argument, which is the predicted theta. And we obtain the loss value. We can do a training loop with this loss and check the results. Here is the loss evolution. So we train for longer because we have less information, so we need more training loops. And we see that it's decreasing, so we managed to learn. And let's check the normalized Hamming distance to see the performance. And we see it's also decreasing, and but we see that the final value of this metric is higher than in the learning by imitation setting, which is expected because we have less information, but it's still a good result. To conclude, you can check for more information the InferOpt package repository and its very detailed documentation. You can check out also this notebook at this link. There is also a paper coming soon for more details about the package. And finally, you can check out more advanced application examples by following the links to these 4 repositories, which implements InferOpt pipelines to solve various more advanced problems. And that's it. Thanks for your attention, and feel free to ask any question.